Hi everyone. Today we'll talk about probably one of the most annoying things that comes up on your screen and you can't get rid of. Well, I'm not talking about my presentation, but a low battery alert which tells you to connect your charger, especially when you have something very important to do. So today, over the course of next 15 to 20 minutes, we'll try to see how we can try to get rid of this low battery alert by gaining some new insights into batteries. Okay, let's get started then. I'm sure a lot of you have seen this message on a number of devices these days, such as mobile phones, laptops, toys, even electric bikes and electric cars and buses, which are becoming increasingly popular on our streets. What's the most popular energy storage device? Well, most of these devices have lithium-ion batteries in them. Why are they so popular? Well, that's because they weigh less and at the same time they store quite a lot of energy in them. They're also relatively safe to use and can be manufactured on a large scale, making them cost effective. Well, to some extent. They're still quite expensive though. The last 2 points have a question mark on this because this is a relatively new technology and we haven't quite figured out how to make them 100% recyclable and sustainable. So there are some great advantages of lithium ion batteries, but there are still quite a few challenges that we need to address in order to solve the problem of energy storage. So what are these challenges? The first one is the capacity, which is basically asking how long can you use a mobile phone on a single charge? Maybe for 1 or 2 days, depending on how you use it. So given the weight and volume, which is fixed for a mobile phone's battery, how long can you use it on a single charge is what is going to decide the capacity, right? So that's an important factor. You can also look at as how far can you drive your electric car on a single charge? Yeah. What about the next one, the lifetime? How many times can you charge and discharge your mobile phone before you have to get rid of it and get a new one? So it can be up to 3 years or maybe even up to 5, depending on how you use it again. So lifetime and increasing the lifetime is also an important challenge. Cycling rate. How quickly can you charge your mobile phone? Up to 80% in under an hour, or even half an hour, or even 5 minutes. Like how quickly do you want it to be charged? That's an interesting challenge, right? What about safety? What happens if the battery is accidentally damaged or punctured? You wouldn't want it to burst up into flames, which is what we have seen in a few batteries these days. So we need to make sure that they are extremely safe to use whenever they're put into electric cars or even mobile phones. What about the environmental impact of the batteries that we use? Where do the raw materials come from? How are these batteries manufactured? What is the carbon footprint of the manufacturing process? Can they be recycled? Can we recover some of these elements and put it back again so that we are kind to the planet and everyone living on it? So these are some of the important challenges that we need to address. And one way of trying to make better batteries is to change the chemistry, to play around with the elements and the amount of elements that are present in these batteries in order to make them better batteries. One such chemistry is a nickel, cobalt, and a manganese chemistry, which has relatively low cobalt content and has a high nickel content. This could be for a number of reasons, such as economical, environmental, or even ethical, depending on how and where these elements, particularly cobalt, is sourced. How is the cobalt mining industry affecting people? That's an important question to ask. But anyway, coming back to our chemistry, we see that this particular chemistry works quite well. It has a high energy density, high specific capacity. So it's a good way going forward. However, it comes with a bunch of degradation issues, which we haven't understood yet. Okay, so we as scientists and engineers need to design some experiments to study these degradation mechanisms and gain insights into the world of batteries to make them better. Okay, so I'll try to go through a few of these experiments or studies that we can do to understand batteries better. The first one, my favorite of them all, which I call the ultimate battery test, is here. Okay, so I'm going to play a very short video which has basically two batteries. There's one on the left-hand side, which is a battery that has gone through a few cycles. It has probably gone bad. The one on the right-hand side is a new battery. Let's try spinning the right one. It doesn't really spin much, right? It's like sliding around. But the one on the left kind of spins like a top. All you need is a little push and it's spinning quite well. So what's going on here? Well, before we try to understand why do they spin, I think it's a bit of a joke to call it the ultimate battery test, but it's a very simple test to do, right? If you can actually take out the battery from your phone and then, if you can spin it like this, and if you see the difference in the way they spin, you can figure out what's going on in them. So what's actually going on? When a battery goes through a number of, particularly lithium-ion battery goes through a number of charge-discharge cycles, it releases gases, which makes the battery bulge in the center, and that reduces the friction due to spinning, right? That reduces the friction to spinning by decreasing the contact area, right? So that's why batteries which have gone through a number of cycles or which have probably gone bad can spin quite well, okay? So that's a very simple experiment that we can do. What other things can we look for to see if a battery has gone bad? Maybe the temperature, right? So if you can measure the temperature, you can say if the battery is overheating or not, and maybe that's the sign of a battery that has gone bad. What about discoloration or marks on the battery? Or what if the low battery indicator pops up way too often, even though you think that you're using your phone or your laptop at a usual level, for what you used to do over the last 1 year or so. So these are some of the other indicators that we can look for. So what experiments can we do to, either measure the temperature or, look for these indicators? So these characteristics or some other characteristics that we can look for are, like spinning, which can be done with an unaided eye. You can also use a light microscope to look for any signs of cracks or rust or, oxidation in the packaging, right? So this can be a sign of, the battery that has gone bad. What we're going to talk today is about an electron microscope, which opens up a world of new possibilities. Okay, we'll see how does that in the course of the next few minutes. But I want to tell you about one key difference between an electron microscope and a light microscope. You know how you use light to see things in a light microscope, while in an electron microscope you use electron to see things. Okay, so that's one of the main differences. But why do we need to use electrons? Well, that's because using light has its own limitations, especially on the resolution. Can you see atoms with light? Not quite. But here's an image that is captured from an electron microscope. If you have a look at this scale bar, which says 1 nanometer, which means that this black bar over here at the bottom is 1 nanometer in length. So this image is taken at a nanoscale, right? And these blobs or dots that you see here, they are basically columns of atoms. And you can actually see that they are dissolved. They are very well dissolved, right? So you can actually measure the distance between the center of these spots and say how far away these atoms or these columns of atoms are to each other. So that's the kind of information, that's the kind of detailed information that you can get from transmission electron microscopes, right? And this image was taken from one actually. And this is what a transmission electron microscope looks like. And here's the person standing next to it, just to give an idea of how huge these machines are. They can take up the whole room, right? So if you come down to Cambridge someday, you can see quite a few of them being used to capture images like this at an atomic scale, at a nanoscale, that gives you a wealth of information to study materials. Okay, so what happens inside? So what happens inside an electron microscope? So here's where we start the story of an electron meeting matter, wherein we are trying to understand what happens when an electron meets matter. Some of them might just pass through as if nothing happened. Some of them might lose energy, and others might diffract. And there might be some electrons which can create new electrons on their own. And they might even make matter radiate, or like the material gives out X-rays when it interacts with electrons. So a number of things can happen to electrons, or a number of things that the electrons can do to matter when it meets them. Let's look at each one of these, okay? So in the first case, if you have an incident beam, okay, which is coming down onto a specimen like this, and if the specimen is thin enough, then you see that the electrons just go to the other side, right? So this is what transmission is, wherein electrons coming on one end are transmitted to the other end as if nothing happened to them. So this is what we call a direct beam imaging mode, wherein we can study the thickness of the specimen. If the specimen is too thick, then we can say that, oh, not many electrons pass through it, and hence the image is not too bright. Right? So this kind of gives you information about the thickness of the specimen. And this is in a very simplistic sense, the way I'm trying to explain what happens to an incident beam when it's, interacting with the specimen. Okay. So this is what happens when they just pass through. But what if they lose some energy? Some electrons, when they interact with the specimen, might lose some energy. And in order to measure that, you can put in what's known as a spectrometer, which measures the energy lost by these electrons, somewhere close down over here. That gives us information about what elements are present within the specimen. Not only that, if you're able to separate out these electrons based on the energy of them, then you can also, construct images which will give you information about where they are present as well. For example, what we see here is a zero loss image that is basically from electrons that haven't lost any energy. And you see some carbon nanotubes, and notice the scale bar here, they're really, really small. But it's hard to say what's present in them, right? But in this energy filtered TM image on the right hand side, you see that there are some specks of green nitrogen. And this tells us not only what elements such as carbon and nitrogen that are present in your specimen, but it also tells us where they are present within your specimen. So it's almost like a map which tells you where you can find these different elements in your specimen, and that makes this technique incredibly powerful, right? So you can figure out what elements are present and where they are present. Okay, so this is what happens when electrons lose their energy. What about electrons that diffract? Okay, here are two images, one taken at a high angle. So this is basically the angle at which you're collecting these electrons, and the next one is at the low angle. Watch this small space over here at the bottom right-hand corner, where it looks like there might be something present, and it's almost invisible, right? But the same region, wherein the image is taken at a low angle, you see that that lights up quite well. So depending on the angle at which you collect these electrons, and depending on how much they have diffracted, you can get different information from the same specimen. And that information might be able to help understand what's going on or what is present in your specimen. So maybe whatever was present here was diffracting more or less depending on the material that was present around it, right? So that is how you can make use of the diffraction information depending on what angles you can collect the electrons, and then use it to study your specimen. What you can also do is you can record images such as these, which are basically diffraction patterns. You could just sit and watch them all day because they're very beautiful symmetric images wherein you have spots at different distances and different angles from each other. And you also see a symmetry, right? And all this gives information about the way the atoms are arranged in your specimen. So you can make use of the diffraction information to study your specimen. What if the electrons that interact with your matter give out X-rays? Okay, so we have again an image here, which is taken in a transmission electron microscope. And again, we see some blobs, right? So there are some arrows pointing at some of these blobs. But it's hard to say if they all belong to one single element or if they're about different elements, right? But by capturing and measuring the energy of the X-rays that come out of these atoms or these columns of atoms, we can get images like this, which tell us that, oh, where there are these pink spots, we have more tungsten there, and where there are these yellow spots, there's niobium there. So what we saw earlier was that we could, identify the elements that are present. And in this case, we can also map them out and say, oh, at this atomic position, there's tungsten, and at this atomic position, there's niobium, or there's more of one in these spots than the other. So this at an atomic level tells us about what element is present, where it is present, and also to some extent how much of it is present if you're able to do the quantitative analysis of that, right? So this is a very powerful technique that way. So I can keep going on about what electrons do. They can create new electrons, they can scatter back, and it's a bunch of different things that can be done with these electrons by capturing them and measuring the data. However, I think I should stop telling the story of an electron now and give you a comprehensive picture, right? So if you have an incident beam on a specimen and some of it just passes through, you can put a bright field detector and then see what's going on to those electrons and understand what's present in your specimen that way, or maybe regarding thickness of the specimen. If you put in a high angular detector, then that gives you a different bunch of information, which is proportional to the atomic number. You can measure the energy loss, and that helps you to figure out what kind of element is present or what is its oxidation state, for example. Right? So this is a kind of summing up all the different things that happens to an electron and how you can make use of it to study your specimen. So if we keep continuing with the story of the matter, I think you will at one point try to stop me and ask, I mean, so what? Like, that's all great, but why are we, going through all this? Well, that's because all these things that we have learned so far can be used to study batteries, right? How can we do that? Well, let's see what a battery is and how it operates. So what we have here is a cathode and we have an anode. What's present in lithium-ion battery are these spherical white blobs or atoms or ions of lithium, which move from the cathode to the anode when you charge and when you discharge, right? So that's what happening in a battery when you're charging and discharging them. So it is very important to note that the structural integrity of these layers, it's basically the cathode and the anode, it affects the movement of lithium ions, and hence it also affects how much energy can be stored in your battery, right? So let's keep this in mind and see what we can do using an electron microscope. Here's an image of a pristine nickel, manganese, and cobalt cathode, which are in the ratio of 8:1:1. Okay, so this is an oxide. And when it says pristine, let's take it as like a brand new battery. It's just out of the pack, and this is what you have over here. And what we have on the right hand side is an aged specimen. Aged as in it has gone through a few cycles of charging and discharging. Maybe this battery has already gone bad, in some sense. But we need to see how they're different from each other, right? So in the first image that we have over here, which we have obtained from transmission electron microscope, and we have done some processing on it, we see that there are these rows of atoms, right? So you can see 4 rows of atoms that are present over here. We see that the same 4 rows of atoms are also present on the right-hand side in this specimen as well. But we also see is that there are 3 additional rows of atoms present between these 4 rows of atoms, right? So these are pointed by these arrows, and this tells us that the material on the left-hand side is different from the one on the right-hand side at an atomic scale, right? So it almost looks like there's an extra layer of atoms, or there's something present here at the surface, and we call it a rock salt phase or a new phase that is present over here, which is different from what we had seen in a pristine or a new battery material, right? So now that we know this information, which we captured by doing transmission electron microscopy at an atomic scale, what can we learn from it? Maybe this extra layer of atoms or this phase that is present in your aged or your battery that has gone bad or is going bad is straining the nanostructure, right? So because you have these extra atoms that are present here, a new phase that might be straining the structure at a nanoscale. Maybe it is impeding the movement of lithium ions and hence the storage and removal of these in the cathodes and in the cathode that we have over here, right? And it might also limit the maximum state of charge of the batteries that way. So this kind of a study that can be done at an atomic scale helps us to know how battery degrades and how these new phases are formed, how does it strain the nanostructure, how does it affect the maximum state of charge. And all this gives information on how the battery is going bad. Okay, so this is just one example of how we can make use of electron microscope and then understand what's going on in batteries when it is in a new state and when it has gone through a few cycles. Okay. So I think this is what you've all been waiting for, some tips to get rid of the low battery alert, right? So we have learned a bunch of things about, what we can do with an electron microscope and how we can study battery materials. So just to, recap that, we'll see that we need to do certain things in order to make the battery last longer. And this is the background information we need to know. Lithium ions moving from cathode to anode and back. And using electron microscope and a few other techniques, we have figured out that the structure of the cathode looks something like this. There are lithium ions, there are transition metal ions, and there are oxygen ions that are present within your structure, and it's a layered structure. Okay. So now imagine the process of charging and discharging. Okay. Imagine you're charging and you're removing a bunch of lithium ions from the structure. Now, if you're taking out a lot more of these, then as you can see, you're essentially destabilizing the structure, right? Because there's like a row of atoms that are missing, and or a row of ions that are missing, and that can lead to a cathode that is not stable anymore. So what does this tell us? It tells us that if your battery is at 0% charge or at 100% charge, then it's not good for it. So you need to avoid, letting your battery drain out completely to 0% or charging it fully to 100%, because either way, if it's working in the H streams, it's not good for your battery. Okay, so to make your battery last long, you need to charge it up to maybe up to 70 or 80%. But never let it go below 20 or 30%. Try to make sure that your batteries, whether it's on phones or cars or even in your laptops, if they're lithium-ion batteries, you need to not overcharge them or let it drain out completely as well. Okay, that's the first tip. Now, what happens if you're trying to insert and remove these lithium ions way too quickly? Okay, that can also lead to destabilizing the structure, right? So you need to also avoid fast charging, unless you're like in an absolute hurry. I know it's a matter of convenience to, charge your phones or, cars really quickly, but the fast charge rates have a detrimental effect on the lithium-ion batteries. So, based on the structure that we have found out from the electron microscopy and other characterization techniques that we have done, we can, come up with some ways of trying to make your batteries, last longer, right? So these are a couple of examples and a couple of tips that we have, gone through this. I'm sure you still have a lot of questions, right? Like, that's all great, but how do we, make the materials to be electron transparent? Because if the materials are not electron transparent, then be it battery materials or whatever it is, you won't be able to, transmit electrons from one end to the other, speaking in a very simplistic way. So how do we make that happen? How do we measure the energy of electrons? How do we separate these electrons into different bands based on their wavelengths or energies? All right, and how do we capture the X-rays that come out of the material when electrons interact with them? And how do we identify the elements? How do we study the arrangement of atoms when you're looking down in a particular direction, whether it's a square or a hexagonal pattern, or if there's no symmetry at all? So that tells us about the crystal structure, right? But how do we go about doing that? How do we make movies with electrons instead of light? So if you see that nanostructures are moving, just like you can make videos with light, you can also make videos with electrons. And that is like a live feed, or like capturing things at a real time, like a live telecast of what's going on at a nanoscale. How do we do that? Well, in order to answer all these questions, why don't you just all come over here and find out yourself? Okay, I think that's it for the end of this presentation. And